we're going to continue on here, wrap up the nuclear chemistry chapter, I think, and then roll into the final stuff we're going to talk about as we've hit the final week of the class, which is good. All right, so we've been talking about, obviously, nuclear chemistry here, and last time we talked about, I think, sort of kinetics that involve nuclear chemistry, and remember that all radioactive decay follows first-order kinetics. And as we saw, pretty much, although they do sometimes use different symbols for nuclear chemistry, it really is the same sort of equations that we used in like that first kinetics chapter that we did for first order. And the two that are mainly used is, again, the integrated rate law, which is natural log of A equals natural log of A naught minus KT. And also the half-life equation for first order, which again is natural log of 2 divided by K. Although K is the rate constant in the sort of nuclear chemistry is referred to as the decay constant oftentimes. Time is still the same. As we talked about, we do want to make sure unit-wise that these guys, in terms of the time, are the same. The one main difference that we did see in these type of problems, which is a little bit different than maybe some of the ones that we did in kinetics, is in terms of the concentrations. Again, they don't really have to be molarity. They really can be any type of unit. They could also be a unit of radioactive decay, like we saw in some examples. They could be percentages and stuff like that. So as long as those guys are really the same units, you could really throw it into this equation and everything should come out okay. The other thing that you very commonly see in this type of problem is a lot of times, because it's radioactive decay, they will give you the half-life. And a lot of times you'll need to use that to get the decay constant and then kind of go into that equation. So a lot of times these equations are sort of used together to do that. We talked about nuclear binding energy, and that's sort of the difference in the mass between sort of the isotope itself and really the particles that make up the isotope, what's in the nucleus in the most part, which are protons and neutrons. And that little bit of mass gets sort of converted into energy. You can use Einstein's equation equals mc squared to do that, where this is what is referred to as the mass defect. And again, the mass defect is that difference in the mass really of the protons and neutrons versus the mass of the isotope. You could go into this equation, and when you do, you end up with units of AMU meter squared second squared. You do need to kind of get it into a joule basically from here, and you could divide by Avogadro's number to the 26. That will get you to kilograms up on top, and that will give you units of kilograms meter squared second squared, and that is equal to a joule. So if you kind of take Einstein's equation, that is the pathway there to get to the binding energy. Usually we do at the end there divided by the number of nucleons, which is basically like the mass numbers, basically your particles in the nucleus. Another approach is you could take the mass defect and basically use the relationship mega electron volts to AMU. 931.5, I believe. And from there, that will give you another common unit, which is the mega electron volts. You could also divide it by the nucleons. You could also go from mega electron volts to joules through that conversion there, 1.602 times 10 to the minus 13. And you can convert it at that point. So there's kind of two routes to take. And again, you can take either one. Nuclear binding energy per nucleon, as we talked about last time, is another measure of stability. So the larger the binding energy per nucleon, the more stable that isotope will be. So that, again, is another sort of measure of stability. Any questions on any of that there? All right, so let's continue on then, just to finish up the last little part. Nuclear transmutation is where you sort of, in a lot of cases, will shoot a particle at something, and obviously it's not going to be happy to do so. So it oftentimes will sort of transform into some other particle. You can do that by a particle accelerator. It's got a magnetic field and electrical sort of field that gets the particle going, and then you shoot it basically at your target there. These are where we get a lot of those guys on the bottom of the periodic table, those man-made sort of elements like nobelium, right, rutherfordium, all those kind of guys. Again, they're all basically generated a lot of times by shooting some type of particle like a neutron, an alpha particle, something like that, that will generate these sort of new man-made type elements like Einsteinium and stuff like that nature. This is also sort of a pathway for fission to occur. And remember that fission itself can occur spontaneously, and fission is basically the idea where you have this unstable nucleus. It will split off into two new nucleuses. It will also give off a number of neutrons and a lot of energy that will come off in a sort of fission reaction. You can sort of make this happen the sort of the same way by sort of shooting a particle. So for example, here, if we shoot a particle here like a neutron over at a uranium-235, it will become unhappy, become like a bowling pin here. And then basically it will separate out into two new nucleuses. Like I said before, it will also generate several neutrons in the process and usually a lot of energy associated with that as well. And as you can see here, and as we maybe mentioned earlier in this chapter, the energy that you get per mole of uranium is like times 10 to the 13, which is a pretty big amount of energy that's released. If you compare it to a combustion of coal, it's like 10 to the 7. So you got a lot more energy in this type of sort of reaction. Again, because we're playing with everything sort of in the nucleus, so that's going to generate a lot of energy sort of moving around. The reason for the comparison of sort of coal to sort of uranium is this is the reaction that is used, say, in nuclear power plants. And in traditional power plants, they burn coal a lot of times to get energy to do so. And when we do have sort of these fission types of reactions, you don't always necessarily always get the same two products that come out, but there are certain products that do very commonly come out in terms of their mass number. But again, it's not always an exact science that you always get sort of the same two guys that will come out. So you can get different products that are formed as a result of these sort of fission reactions. And again, this fission reaction can be used for things like, say, I can create a nuclear chain reaction, for example. And this reaction can sort of continue to feed itself. And the way that happens is obviously, since we start the reaction with a neutron and it causes this guy basically to split off, each of these guys then will form some neutrons, which can keep this reaction sort of going and sort of extrapolating and expanding. And the minimum amount of material needed to really keep this fission reaction going is what is referred to as the critical mass. And when you don't have the critical mass, sort of a non-critical amount, you're able to sort of contain it a little bit. It won't be able to kind of just continuously keep going. If you do have a critical amount of it, you could keep this fission reaction going, again, because what starts it is also produced. So it just allows this reaction to keep feeding itself if you have the right amount. That, for example, is sort of how a nuclear sort of weapon works. They have sort of a subcritical mass of uranium that can go through a fission reaction separated. When it does crash, it explodes, and then it kind of completes the mass there needed. And at that point, you'll have the right amount of mass to keep this fission reaction basically going and going. Obviously, every time it goes, it's going to split off into new nucleuses, which could be radioactive, giving off particles and radiation, obviously, as it continues to do so, and a lot of energy as well. So if you have a critical mass, you can keep this reaction just kind of keep going and going, and a non-critical way is sort of keep it under control. As I mentioned before, it is also the reaction that's used in a nuclear power plant, and nuclear power plant versus sort of a traditional power plant. They basically all sort of work very similar. You basically have water and you heat the water And when you heat the water, you create steam. Steam goes out to the turbines, and you get lights eventually and all that good stuff. And really the difference between, say, a nuclear power plant and a traditional power plant is really the source of how you heat the water. As we saw on that last sort of slide there, coal is traditionally used. And when you burn coal, the heat from that will heat the water and so forth. In a nuclear power plant, it is a fission reaction that is used to basically heat it. And here's sort of a cutaway of a nuclear reactor. We have basically our water here that's going to get heated. We have really the nuclear fission sort of chamber, if you will, where the fission reaction is going to occur. And inside these fission reactions, there's a few things. There's fuel rods. So you have these little fuel rods, and these fuel rods have, like eraser size samples of uranium, basically. And you got a bunch of these little uranium sort of pellets in there that's going to allow the fission reaction to occur. And as that fission reaction occurs, there's sort of this insulated water pipe that runs through the other water guy. And obviously that's going to heat this water pretty hot. That's going to heat this water pretty hot. And that's going to in turn heat this water hot, which will create the steam that again could go out to be used to power everything. Now, the nice thing about water and steam is if you cool steam back down, you get your water back, which is why very often nuclear power plants are built near large bodies of water so they can use it to cool down the steam and sort of regenerate the water. Like over there in San Onofre up the 5, right? We got some nuclear power plant right there. And it's by an ocean. If it's not near some big body of water, a lot of times they'll have very big cooling towers of water to use to sort of do that process as well. So why does this reaction not go sort of out of control and sort of make a chain reaction? There's a couple of sort of safety things that are sort of put into place. One of them is they try not to use a critical mass of uranium. So they use a non-critical mass of uranium, which keeps the reaction sort of under control. In addition, they also have these control rods, which are inserted inside here where the fission reaction is happening. And control rods are sort of soaked with things like cadmium, for example. And cadmium is a good neutron absorber. So you got this control rods that are really good at sort of grabbing up neutrons. That's important because the fission reaction occurs by basically a neutron, and it also makes neutrons. So if you have these control rods, which can kind of take some neutrons out of the reaction, that's going to be less neutrons are going to be able to sort of start the reaction again, and that will keep the sort of fission reaction under control, since it is a neutron that starts it and produced. And if you take some of them out, that will keep basically everything under control. Clearly, a lot of times the nuclear part is tried to kept away from obviously the sort of non-nuclear part, if you will. Now, there's obviously benefits and downsides to both of these sort of processes. Obviously, if you burn coal, there's a lot of waste product that occurs. Also, to get the coal as well, sometimes that's can destroy a lot of things. Obviously, although the fission reaction is cleaner in that sense, it does also, though, develop a lot of waste products that are radioactive. Creates a lot of radioactive isotopes that stick around for a very, very long time. And you have to decide, like, what do you do with all that stuff? Who keeps control of it? Where do you store it? For a lot of years, nobody wanted it anywhere. So for a lot of years, nuclear power plants would, for the most part, kind of just store everything on their sites because nobody wanted it traveling to places through their towns and stuff like that. So years ago, I think they finally built a big thing in Nevada where they have put a lot of that type of stuff. But it does create a lot of waste products, and it creates a lot of what is sometimes referred to as spent fuel. And spent fuel is basically the sort of products of a fission reaction. And the reason spent fuel is also part of the hazards of it is they are very radioactive as well. And again, they stay basically around for a really long time. As you can see here, if you just kind of look in this area, that's like 10 to the 3 years of storage time. So that's a very long time of storage time to have to store these things. And again, it creates things like who keeps track of it, what do you put it in, and all that type of stuff. Now, fusion, on the other hand, is a reaction where fusion, on the other hand, is basically a little bit different than fission. Fusion is when you take two sort of smaller isotopes and put them together to make one. So you kind of combine them, and it occurs at very, very high temperatures, like you're on the sun type temperatures. That's basically that type of temperature. So this occurs at very, very high temperatures. You take two smaller guys basically and fuse them together, fusion, and you make a larger sort of isotope. And again, usually happens at really, really high temperatures, which is why on all those movies and stuff, they always want the guy that can do cold fusion or something like that. So they can do it at normal temperatures, this sort of process. Now, we also use radioactive isotopes in medicine, and one of the nice things about sort of, I guess, radioactive isotopes is, although they are radioactive, they will perform, for example, in the body, basically the same thing as, say, a non-radioactive isotope. So you could use them in a lot of applications. You could use them as tracers where things are going. You could use them in scans to light up things and see things. So for example, there's sodium-24 is a blood flow tracer, iodine 131 for your thyroid gland, fluorine 18, some imaging, and also iodine 123 for some brain imaging as well. Now, obviously, when we use something in medicine, typically you want something with a smaller half-life. Otherwise, your follow-up appointment is going to be very, very far down the road. So usually we're not looking at years and years of something that has a half-life of years. Usually things hours, maybe minutes, and that type of stuff is used. They also sometimes will implant radioactive sort of seeds and tumors and stuff like that to try to shrink them. And here's a bone scan with technetium-99. And again, it just allows things to be basically highlighted in those processes. This is something that you would be familiar with if you did anything with radioactivity. This is a Geiger counter. And a Geiger counter basically has an anode and a cathode. And it really creates sort of a voltage as it looks for sort of radioactivity. And it will usually give an audio sort of beep, beep, beep type thing. Also usually having like a needle or something like that, you can see it go up and down. And you usually will use this a lot of times when you're working with radioactivity, just to make sure your surroundings and everything has not been sort of contaminated. In addition, if you work with radioactivity, I'm going to mention before, a lot of times they will have you wear like a little ring and maybe a button as you're working with it. And every so often they'll sort of expose it to see how much exposure the ring and the button got, and that obviously would be kind of the same exposure you got. And they might tell you need to sit out at work for a while there to relax a little bit. Obviously, if you're ever working with radioactivity, like we mentioned, it's always a good idea to know what type of emitter it is, so you could take the proper precautions. Sometimes people don't tell you the proper things. And again, you want to make sure that you limit your time exposure is also a very, very good idea as well. Now, if you took something like a Geiger counter, and something you commonly hear sometimes when people use it is if they hold it up, it will make a noise because there's background radiation. And it shouldn't be super loud noise, but it will, kind of beep, beep a little bit. And a lot of times people say, it's just background radiation. And we do have sort of background radiation depending on sort of what we're exposed to. A RAD is sometimes referred to as a radiation absorbed dose, and a REM is an equivalent for a man. It's basically the RAD times a factor. As we saw earlier, these guys penetrate, a lot further. For example, gamma rays and beta rays penetrate a lot further than, say, an alpha particle, which is why you could get a little bit more exposure to an alpha particle than, say, something that's emitting a gamma or a beta ray. We get just exposure from cosmic rays, air travel, X-rays, nuclear waste, if you happen to live near fallout weapons testing, all those type of things do contribute to, sort of our exposure. So there is sort of background radiation. We are exposed. And again, the key is if you're ever working with it, take proper precaution and obviously limit your time. Is usually a really good idea. Any questions on any of that there? Those are strawberries and a good way to end it, I suppose. Yeah. All right, that is the nuclear chemistry chapter. Any questions on that? All right, so what we're going to, yeah. Everything. um, you need to know how, obviously, all the balancing nuclear equations, the decay series, right, with the kinetic stuff and the binding energy and all that. So most of the chapter, I would say, for sure. Yeah. All right. We're gonna do let's start last chapter here, a little organicness, right? We'll just say we did, I suppose. Why not? All right, so this is the last one of the season here, a little organic chemistry to end it out. We'll just keep going for a bit on it and see where we get to. All right, so organic chemistry, pretty much if you pick up any organic book, this is the first sentence. The study of carbon compounds is usually, that's usually like the first sentence you can find in every organic book. Is basically organic chemistry is a study of carbon and carbon-based compounds, as you can see right there, that contain carbon. And the major sort of connection of organic compounds are carbons basically attached to carbons. And off of those carbons are hydrogens, basically, a lot of times. And that's really your basic sort of organic connection. Carbon to carbon, carbon attached to basically hydrogens. A lot of products are such as clothes, foods, and medicine and gas are made a lot of times of organic compounds. Organic compounds are composed of covalent bonds. Obviously, we got non-metal action here, so we're going to be sharing electrons. Their properties differ greatly from ionic compounds. And one of the main things here is obviously, since the basis of organic chemistry is carbon-carbon, that's a non-polar bond. And also the carbon-hydrogen bond is non-polar as well. And that's a difference in electronegativity of about 0.4, which is non-polar. And this one obviously is a difference in electronegativity of about 0, which is obviously non-polar. A reminder that a polar bond is a difference in electronegativity of like 0.5 to below 2. And a non-polar bond, basically a difference in electronegativity of less than 0.4. So 0 basically to 0.4 basically. And non-polar bonds, right, means that electrons are shared equally, which means there is no negative side or positive side to that bond. Polar bonds, right, as you know, it means electrons are shared unequally, and there's a positive side and a negative side to that bond because of the unequal sharing of electrons that are basically happening. So some of the main differences between sort of inorganic compounds, which are things, say, like ionic bonds and ionic compounds, like sodium chloride, and guys that are sort of organic, is organic guys exist which much weaker intermolecular forces. And for the most part, most organic molecules are pretty much going to be rolling with dispersion forces in terms of their intermolecular force. And if you remember what dispersion forces are because they are nonpolar, they basically has to rely upon something happening for them to interact with each other. And that is what is sometimes referred to as polarizability. And that means that if these are two nonpolar molecules, basically what could happen is the electrons, say in this first guy, will maybe all pile up to the right. And that will create temporarily in the first guy a separation of charge of its electrons. That's going to cause the electrons in this guy to head in the opposite direction. And that will then temporarily cause a separation of charge in the other nonpolar molecule. And if you remember, all intermolecular forces are pretty much opposites attract, positive and negative attraction, and that's going to temporarily give them a way to interact with each other. And it's temporarily because, as soon as those electrons kind of go back, they're going to fall apart and then remake some new ones and stuff like that. So there's this sort of, in a dispersion force situation, something needs to happen to allow really those guys to interact well with each other. And that's why this is a pretty weak intermolecular force. And that's different than, say, an ionic compound. An ionic compound is pretty much the strongest interaction you could get, that electrostatic attraction, which is actually more of an intramolecular force within the molecule. And that's a super strong force. So one of the major differences that you see between, say, something that's inorganic and something that's organic is a lot of organic molecules are gases under normal conditions. If you think about sort of the early organic molecules, there's methane, propane, butane, and so forth. So those are all gases under normal conditions. And that's because pretty much if you sneeze at this guy, it's going to have no problem basically to hop off into the gas phase because it's not being held together very tightly. That's also why things that are maybe not in the gas phase, that are organic liquids and stuff like that, they're sometimes referred to as being very volatile, which means that they could go into the gas phase really, really easily. It doesn't take a lot for that to happen. They have very low melting points and boiling points because of that, and they're able to basically just kind of go into gas phase. That's why when you take organic, they stick you in a fume hood when you do your lab work, because a lot of the chemicals that you use pretty much can just go straight into the gas phase. And if you have something like a Bunsen burner nearby, that's not really good as well, since a lot of them are flammable as well. So because basically a lot of organic molecules are held together by these sort of weak dispersion forces, they a lot of times are gases. They have very low melting points and boiling points. And that's super different than, say, sodium chloride, which is held together by this intramolecular force of electrostatic attraction. It's like, again, the strongest sort of attraction that you could get. And you could heat the heck out of that, and it's probably not going to go into the gas phase. It'll start to melt before it would actually break apart and go into the gas phase. So it's held together really, really strongly. And that's why obviously sodium chloride or salt is usually a solid at room temperature. Now, all organic molecules do contain, as I mentioned, carbon. And a reminder of carbon wants to make 4 bonds pretty much. And that's a super important thing to remember when you're doing organic chemistry. Carbon is group number 4 on the periodic table. It has 4 valence electrons. It pretty much wants to make 4 bonds always. It should never make more than 4 bonds. As you may know, it cannot go past the octet rule because it is group number, carbon is period 2, which it is n equals 2. And on the n equals 2 level, you have what orbitals available? You have s orbitals and p orbitals only. Yeah. They do not, carbon does not have any d orbitals available, and that is what is necessary for things to go above 8 and do the expanded octet. So carbon can never go above 8. It should never have more than 4 bonds. I say that because when people first start doing organic chemistry, is they all the time like just keep throwing bonds on carbon. It's before you know, it's got like 30 bonds on it, and people just keep drawing lines to carbon, stuff like that. So should always have basically only 4 bonds. And for the most part, if there's no other elements present, pretty much hydrogen is going to be, the other element that's going to be there. And usually you can think about, okay, how do I finish up a molecule? You think about carbon and getting into 4 bonds. You can figure out how many hydrogens will get carbon to 4 bonds, and that time will get you the right amount. Hydrogen, though, on the other hand, is something that should always be on the outside, should only have 2 electrons. It follows the duet rule, and that is, again, because hydrogen only needs to get to helium, right, to have a noble gas configuration and be stable. So hydrogen should never go over too. I say those are probably two of the most common things that people screw up on when they first start organic is they draw way too many bonds to carbon and they put like too many bonds to hydrogen and dots around hydrogen and triple bonding hydrogen and stuff like that. So you should never do any of those things. And again, this is basically your basic setup. That is methane, which is the simplest organic molecule you basically could have. Carbon forms single bonds, double bonds, and triple bonds with other carbon atoms. And it does make different types of organic molecules based on that. So for example, you can have a carbon that will make a single bond with another carbon. This is a group of organic molecules which are known as alkanes. They are the basic sort of group of organic molecules. And by the way, when we look at organic molecules, there's really a part of the organic molecule which is sometimes referred to as a functional group. And a functional group is really sort of the part of the organic molecule which makes it a certain type of organic compound or classification of organic compounds. There are different sort of functional groups, and the presence of those functional groups gives you these different types of organic molecules. So for example, here, some people might not say this is a functional group, but basically a carbon-carbon single bond is the functional group of an alkane. And alkanes have a general form of CnH2n plus 2. Which means that, for example, if you had one carbon, which is what N is equal to, 2 times 1 is 2 plus 2 would be 4 hydrogens. And again, this is known as methane. This gives us, if we drew something like methane, for example, a carbon atom here, which has 4 electron pairs and 4 bonds. That is our friend. What type of geometry? That is tetrahedral. Yeah, that is a tetrahedral molecular geometry of 109.5 degrees, right? That is also, if you remember, when we talk about carbon atoms, we talk about sometimes hybridization. This carbon would be what type of hybridization? This is a sp3 hybridized carbon here, right? By the way, if you're not sure how to do hybridization, the very simple way to do it is like this. So you know there's 1 s orbitals, there are 3 p orbitals, and there are 5 d orbitals. So when you look at, say, a carbon or an atom that you want to apply hybridization to, you basically count up the number of electron pairs. And you count up the number of electron pairs like you do geometry or VSEPR. And when you come across a single bond, a double bond, or a triple bond, it really doesn't matter. They all count as 1 electron pair. So when you look at something like what we just did here, as 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. So if you want to know the hybridization, you just start at the bottom here and just make some X's, 1, 2, 3, and 4. That's an S and 3 Ps, and that is the hybridization basically of that central carbon. Now, they can also make carbon-carbon double bonds, which is the functional group for what are known as alkenes. And alkenes have a basic form of CnH2n. And for example, if we looked at for here our C2H6, we could have an alkane that looks something like this. And again, each of these carbons are going to be sp3 hybridized carbons. And this is what is known as ethane, all single bonded carbons. Now, if we take something like C2 in a double bond situation, that is going to give us H4. That means when we look at this guy, it will actually look something like this. And one of the things that you see is I actually had to put on another bond here. And in order to do that, I could not just put the double bond in, because then that carbon would have 5 bonds on each side, which is too many. So pretty much in organic chemistry, every time you slap a bond in between 2 carbons, you got to sacrifice a hydrogen on each carbon. That way you don't go over the number of bonds that you need. And that's what you see there. That is also why the 2 here disappears, because we had to lose 2 hydrogens to make that bond when we look at the general form of alkenes. Surprisingly enough, this is ethane, and this guy would be ethene, E-N-E, because this is a alkene. That's an alkane. Pretty much, as we will talk about, all sort of nomenclature of organic molecules pretty much all involve the alkanes. Everything goes back to the alkanes. Everything goes back to like the single bonded guys. Everything's pretty much based off of that. And that is a really good thing when you start organic chemistry, to make sure you have a pretty good understanding of the names, the formulas of those alkanes, because everything really does sort of fall back to it in terms of naming and how things are sort of approached. But the other consequence of our double bond here is when we look at our double bond here, we now have a different geometry that just developed. We have 1 electron pair, 2 electron pairs. And once again here, our double bond is going to count as only 1. This is going to give us 3 electron pairs. It also has 3 bonds, the same 3 spots. And that's going to give us a trigonal planar geometry. Because of that double bond. It's also known as triangular. That's your bond angle of 120 degrees, again, making the triangle happening basically right there. In addition, because of that, we also hit a different hybridization that occurs, for example, with this organic guy. And if we take a look at it here, get rid of my arrows maybe. So if we look at this, once again, if we were going to do our hybridization, we do have our 1, 2, and 3 electron pairs, 1, 2, and 3, which means that this guy is an S and 2 Ps, right? So sp2 hybridization. By the way, that is the combination of S and 2p atomic orbitals coming together, right? Creates basically hybrid orbitals that are the same shape, same energy, makes for better bonding, and basically accounts for the different geometries that we see going on here. Any questions on that there? Question. In addition, I'll flip the page. We could also make some triple bonds happening. And so carbon-carbon triple bond is a group of organic molecules which are known as alkynes. And it has to have at least 1 triple bond in there. And they have a general form of CnH2n minus 2. So as we just saw there on our previous page, we had our alkane, which was our ethane. We slapped a double bond on there, lost a couple of hydrogens, and we had our ethene. And now what we're going to do here, if we took C2, that will give us H2. We will slap a triple bond in here, which means we need to lose, once again, 2 more hydrogens to allow that triple bond to come in so we don't go over. And as you might guess, this guy is known as ethine, Y-N-E, because it has a triple bond basically in it. Again, here, when we look at sort of the geometry, it also changes. This carbon right here, for example, has 1 electron pair there. Remember, again, the triple bond here counts as 1 electron pair. So that's going to give us 2 electron pairs. It also has 2 bonds, which are the same spots. And again, this would now make our geometry here linear, which is 180 degrees. And in terms of our hybridization, again, you could follow the same thing here. In this case, we do have our 2 electron pairs, which means 1 and 2. So this guy is going to be sp hybridized in this particular case. Questions on hybridization. By the way, some other ones that you learned, probably not going to come across too much in organic, but sp3d, yeah, that is your 5 electron pairs, triangular bipyramidal geometry that goes with that, and your sp3d2, those are expanded octets, which is your octahedral, right, which is 6 electron pairs basically around it when you go there. I would say probably for organic, most of the time it's going to be sp, sp2, and sp3 because it's carbon based, and again, carbon can't go expanded, so you won't really get into those in terms of the other hybridizations. Any questions on that there? Now, speaking of functional groups, why we kind of talked about it, there are different functional groups which basically will, as I mentioned before, sort of turn a organic molecule into a different type of organic molecule, or maybe a different class of organic molecules. And this happens with sort of replacement of hydrogens with other elements, and it can make some other bonds. So as an example here, we ran through a few already. Our carbon-carbon single bond is our alkanes. Again, your simplest sort of organic. Carbon-carbon double bond is your alkene. Carbon-carbon triple bond is your alkyne. You could also have an OH group involved. That's an alcohol. You could also have a carbon, oxygen, carbon. That's an ether. You could also have a sulfur group involved, like an SH. That's what is referred to as a thiol. You could have this carbon oxygen double bond to a hydrogen. By the way, this carbon oxygen double bond is what is referred to as a carbonyl carbon. And that is known as a group of molecules, which is known as aldehydes. You could also have carbon oxygen double bond OH. That's a carboxylic acid, like acetic acid, vinegar, basically. You could also have a carbon oxygen double bond to an oxygen. That is what is referred to as an ester. Those are ones that are responsible for a lot of smells and fragrances that we smell, like bananas and that type of things. You could also have some nitrogen containing group like an NH2. That's what is known as an amine. It also have one that looks like a carboxylic acid, but also has a nitrogen on there. That's what's known as an amide. So this is a number of organic type functional groups, and the presence of these groups will basically give these things some different sort of properties. For example, something with an OH group now will have the ability, for example, to hydrogen bond in certain situations because that OH group is a polar group. And in certain cases, if it's not too big of an organic molecule, because the OH group is there, for example, if you took something like methanol, which is this guy right here. Now, methanol, because it has this polar group where the oxygen is more negative, the hydrogen is more positive, this part of methanol is nonpolar, basically. But because it has this OH group, when it gets near something like water, which also has basically the same bond, it is able to do a little bit of hydrogen bonding with the water, and it actually will become soluble in water because they're able to interact with each other through the same type of intermolecular forces. You might remember the idea of like dissolves like. So things with similar intermolecular forces are able to interact well. So something like methanol, even ethanol, are very soluble in water because they have that OH group and they're not really long. I will say that typically speaking, if you have this sort of polar group and it's able to interact with water, somewhere around 5 or more carbons you start to see the solubility, for example, in their interaction drop a lot. And that's just because the nonpolar part of the molecule gets too big, and that small polar part is too small for it to interact well with water. So usually in organic chemistry, upwards of, it depends on sort of the functional group that's present, upwards of, about 4 or 5 carbons, things can be fairly soluble with water if it has like an OH group or something that allows it to interact. But usually once you get to that 5, 6 or more carbons involved, they call it sometimes steric hindrance. For example, if you had this, and these are all just hydrogens all the way across. Although this guy here does have that OH group all the way at the end. It also has now a pretty giant nonpolar part versus this polar part over here. And it's pretty much going to get in the way, basically, of it being able to interact with water. Remember, for example, for something to interact well with water and be soluble in water and mix well with water, is you basically have to replace water and water interactions with similar type interactions. Water is a relatively small molecule, and you're trying to park this really big non-polar part that's going to have trouble interacting with water in with all the other water molecules. It doesn't really mix. So solubility drops pretty far down when you do that. Now, that's different as well than, if we took something like, not that carbon, there you go. If we take something like this with water, it's going to be non-soluble or insoluble, I guess is a better way of putting that. And that's because, again, this guy's going to do dispersion forces. This one wants to do hydrogen bonding. So there's no real good way for these guys to maintain that interaction, and they're not going to be able to do that. So functional groups are really important. And when you see a functional group in a molecule, like I said, it sort of tells you what type of organic molecule you're dealing with. And it also can change the properties of the organic molecule to being something where it can, like I said, interact perhaps well with water and stuff like that. It also affects things like its boiling point and melting point. So for example, an alcohol will pretty much have the highest boiling point and melting point that you could get, except for maybe this guy. This guy's one of the only things that could beat an alcohol in terms of boiling point. And that's because this guy has actually 2 polar groups. The oxygen is more negative. This guy's positive. This guy's negative, and this guy's positive. So because it actually has those 2 sort of polar groups on it, it actually allows it, when it's with itself, to bind in 2 spots per molecule. And what that means is when it's with itself, it's got a lot more hydrogen bonding happening. It's going to take a lot more energy to break it apart to get it to boil and go into the gas phase. And it has a much higher boiling point. In terms of most things, alcohols, which are right here, because of that OH group, has usually a much higher boiling point or melting point than, say, an alkane, an alkene, or an alkyne are in most things, because they can't do that hydrogen bonding. So if something has that ability to hydrogen bond in an organic molecule, it does affect things like its boiling point and melting point. It typically will increase it because of that. Any questions on that there? So we sort of jumped a little bit, but we'll just talk about some other characteristics of organic compounds. As I mentioned before, methane is the main component in natural gas. And again, it is oftentimes founding in the gas state, a lot of the early ones. Now, organic molecules are also arranged in different sort of orientations. A lot of organic molecules are sometimes referred to as being a straight chain, which basically just means all the carbons pretty much just go straight across. So there's kind of like a straight chain here happening. We also can have organic molecules, much like a tree, for example, which start one way and then just maybe branch off in some other directions and stuff like that. This is what's sometimes referred to as being a branch chain, where you have kind of a main part of it, and then you have these kind of branches that come off. Obviously, there'd be hydrogens attached to all those carbons and stuff like that, but that's what sometimes referred to as branch chains. And in certain cases, what could happen is the two ends could decide to come together and make more of a ring type structure. So for example, here, this is propane, which is 3 carbons in a row. If we sort of have these two guys come together, it will create this sort of ring structure, which is known as cyclopropane. And that's basically the 3 carbons attached to each other. Now, there is a sacrifice, just like what we saw earlier when we added an extra bond. When these 2 carbons come together, they have to sacrifice hydrogens to do that. Otherwise, they will have too many. So if we look at propane, that is C3H8. Our ring type structure, our cyclopropane, is missing 2 hydrogens. So these are sometimes referred to as cycloalkanes, which are basically all single bonded guys. They typically have the same sort of general form of CnH2n. Again, they have to sacrifice those 2 hydrogens to sort of come together. Organic compounds can, again, contain other elements, like I mentioned before. They can have nitrogen, oxygen, fluorine, chlorine. The halogens are very commonly incorporated into organic molecules. And I would say nitrogen and oxygen are probably the other 2 main ones, sulfur a little bit as well. They can have non-bonding electrons or bonding electrons. Again, the octet rule there is still sort of followed what we're looking at. Here are some common patterns for organic molecules. Hydrogen, again, should only have 1 bond, carbon 4. Nitrogen typically will have 3 with some non-bonding electrons, which also gives it the ability, right, to hydrogen bond. If you could find somebody with like a hydrogen that can bond with it, it has that ability to do so. Oxygen, very commonly like that with some non-bonding electrons, but also very common with oxygen is it double bonding to carbon. And again, as I mentioned before, this is what is known as a carbonyl carbon. And again, it is a polar guy in terms of its sort of function. That's also really important in terms of how bonds make and things move around, that sort of polarity that occurs. Most common multiple bonds with carbon. Again, we see that carbonyl carbon there in formaldehyde. And again, giving us some different sort of properties. So let's talk a little bit about some of the formulas that are used in organic chemistry. So in terms of formulas, there is our basic molecular formula. Which is something, say, like C4H10. There's also a way that you can sort of draw that out, which is, do it here, I think. And you could draw out all the hydrogens that are basically attached. This is what is sometimes referred to as the expanded structural formula. You basically draw out all the hydrogens. You could condense this down. So this little guy right here is CH3. Next one is CH2. Next one is CH2. And last one is CH3. This is obviously what is referred to as the condensed formula. Major difference is you really just don't draw off the hydrogens, basically. And very common in organic chemistry is the classic line formula. There it is right there. That is what is known as line formula, I guess, or structure. In line structure, it's really just a basic sort of structure. It doesn't get so confused with all the letters and stuff in there. Anywhere there's sort of an ending, anywhere there's kind of a point, they're all carbon. So for example, if we look at this guy here, this is a carbon. that's a carbon, and that's a carbon, and that is a carbon. And usually you don't put the little red circles, but that is our 4 carbons that is in this guy. Now, also not usually drawn on a line structure is the hydrogens, but it's assumed that at the end, this carbon should have 4 bonds, and it has 1 line coming in, which means technically speaking, it should have 3 hydrogens there. The guy next to it has 2 lines coming in, so to get carbon to 4, it should have 2 hydrogens. Guy next to it also has 2 lines coming in, so to get him to 4, it would have 2, and this guy would have 3 at the end. And once again, though, usually it is just drawn like that with nothing else there. Now, if you see a line structure, and by the way, with an alkane, you typically will get what is sometimes referred to as this zigzag shape. And the zigzag shape is because of the tetrahedral geometry that we talked about. It has that tetrahedral, it's a tetrahedral, so it causes it to do that. If you had a triple bond, it actually will straighten out and you'll have more of a linear geometry and so forth. Now, if you did have something in sort of line structure that is not a hydrogen or not a carbon, you would actually put it there, like you would draw a line and you would see something written there. It's obviously that's a bromine at the end of that. Or, that's a OH group. Now, if you see in a line structure a line drawn there with nothing at the end of it, it is still assumed to be a carbon, which then should still have your 3 hydrogens basically attached to it. So sometimes people see these lonely lines and go, what is that? And it's just like basically, it's really a methyl group is what it's called, but it's basically a carbon with 3 hydrogens at the end of it. You could also do it for functional groups that have like your double bonded to oxygen. That would be like a carbon oxygen double bond. That would be like your aldehyde there, carbon, double bonded oxygen to a hydrogen. So line structure is used a lot. Again, it allows it not to be so crowded with all the letters and stuff like that. If you take a real organic class and as opposed to a fake one, you will use line structures most of the time. Like if you go to 80 and 81, you probably use a lot of line structures. If you take more of a survey type organic class, you probably use more of the condensed formulas and those type of formulas and stuff like that. Those fake chemistry, organic classes, I'm just kidding. Some, like I said before, will again, you could also show it specific things. So if you do have something like in a condensed formula, a lot of times they will draw out, as you can kind of see there, this sort of branch guy that's there. And the reason that they do that is it shows that it's really not part of the main chain. It is sort of something attached to it. As if you incorporated it sort of into here, you might be tempted to write it like this. And the problem with this is, technically speaking, too many bonds the way that's sort of organized. So usually people won't do that. They will still sort of do a little bit of structural in the condensed one to show different groups and stuff attached. To imply that they're not really part of the main chain, that they're sort of attached to it as you go through it. In addition, sometimes there's a lot of long organic molecules that have basically units that keep repeating. So for example, you could have something and in this particular case, there's a carbon, and this is basically just 4 of the CH2 units just repeating itself. So it's just this guy. And then you would have technically these 4 guys in a row. So sometimes those kind of shorthanded up because there's a really long carbon hydrogen chain. That CH2 is sort of very commonly as well. As I mentioned before, skeletal structure is sometimes used. And a lot of those cycloalkanes are oftentimes drawn in line structure. So this is 6 carbons. And 6 carbons in the straight chain is what is known as hexane. And this is in a ring chain, so this is known as cyclohexane. Just like here, little triangle is cyclopropane. A lot of times square as well, cyclobutane. And as I mentioned before, in this sort of structure here, if you got something attached, they will put it out there. This is sort of the expanded structure for this guy here, which is cyclopentanol. This is an alcohol with an OH group there on the end of it. So as I mentioned before, that functional group is really the type of, or part of the organic molecule that's really the most important, as it tells you, again, the type of organic compound it is. It is also important for a lot of different reasons as well. One reason is it is usually takes priority, for example, in terms of how you go about naming that organic molecule. Also, I would say that pretty much most of the reactions that occur with a particular organic molecule, most of the action happens at the functional group part. So where the functional group part is where a lot of sort of the action of the reaction it may go through will actually take place. So in organic chemistry, sometimes people will put R. R represents some type of carbon group that is there, and then the functional group that is next to it. Now, hydrocarbons are atoms that contain only carbon and hydrogen. And as we mentioned before, here are some of those functional groups. An alkane, which again has a carbon-carbon single bond, an alkene, which is a carbon-carbon double bond, and an alkyne, which is carbon-carbon triple bond. There's also a group of organic molecules which are referred to as being aromatic. And aromatic guys contain actually the benzene ring, and the benzene ring looks like this. It is a 6-carbon ring that has 3 double bonds in it. You could draw a resonance structure where the double bonds are on the other side. And sometimes in some books, you may even see it drawn with like a little circle in the middle. And that is because those double bond electrons are delocalized. They're moving around and stuff like that. So anything that has a benzene ring is considered a group of molecules which are known as aromatic. It should not be confused with the one that we just saw a second ago, which is this guy, which is cyclohexane. That is not a benzene ring because it does not have the double bonds. So it's got to have the double bonds to be the benzene ring. Specifically, it's got to have those 3 double bonds to be a benzene ring. So just because it's a ring structure that kind of looks like it is not the same thing. Here are some of those. We'll see how I did. I think I maybe got most of them. Let's see. We have our alkane. We have our alkene, which is our double bond. Our aromatic guy. Our alkyl halide, again, that is where we kind of really substitute out a hydrogen in an alkane, for example, with an halogen, and we'll put it on there. Alcohol, our ether, our amine, and our thiol, which is our sulfur groups. And again, as I mentioned before, a lot of those guys will have this carbonyl group, and it's a really important group as it is obviously a polar group. Because of the positivity of this guy, it oftentimes is a central role in a lot of reactions that occur. So a lot of things will, for example, and we're not going to get into it in here, obviously, but a lot of things when they do, for example, attack, will attack that. A lot of things that are negative will be able to come in and sort of attack the carbon and sort of attach to it through that positive negative attraction, and it makes a really good thing. It is positively charged, which means it's electron deficient. So again, kind of something with some electrons and negative charge can attack it. And it also provides again, a polar group that can interact with other polar groups at that particular point. And there's our aldehyde and ketones. I might have missed a ketone earlier. So a ketone, by the way, is, I think I did miss a ketone, is a carbon-carbon 3-pack. And in the middle is a carbon-oxygen double bond. So a ketone is another very common organic group, and it's got that kind of 3 runs of carbons, and it does have that OH group. Now, there's a couple of things about just when we talk about sort of bonds and how many bonds things can have. For example, this aldehyde here, which has this bond here, because of the presence of the hydrogen in it, it always has to be at the end of the molecule. And that's because if that group was in the middle of the molecule, you would have to attach something to the hydrogen on the other side, and now hydrogen would have too many bonds. So because of that hydrogen that's at the end, this sort of functional group part will always end up at one side of the molecule versus the other. And that's different, for example, than say a ketone, because in a ketone, you need 3 carbons in a row, and it's got to be the center carbon that has a double bond. This double bond or carbonyl will never end up at the end. It's always got to be at least one end. Could be more than one end, but it's got to be at least one end from the end, because it needs to be that 3 carbons in a row with the double bonded there in the middle. Here's our carboxylic acid and our ester as well, and our sort of nitrogen containing groups, our amides. So let's talk a little bit about alkanes. Alkanes, as I mentioned before, are your simplest organic molecules that you can have. Again, in order for it to be an alkane, it does have to have pretty much only single bonds between carbons and carbons. Everything pretty much falls back to the alkanes in terms of naming and other things. So they're really important. They have the general formula CnH2n plus 2. If they are what are referred to as being saturated, that means that when you look at an alkane and if it's saturated, it will have the maximum number of hydrogens that each of those carbons should have. So in this case, because they're all single bonded, the maximum number of hydrogens you could throw on there are 3 on the outside and 2 in the middle. And that is what is referred to as being a saturated hydrocarbon, for example. An unsaturated hydrocarbon, as we will see, basically means that you do not have the maximum number of hydrogens. And that occurs, as we talked about, for example, if I wanted to put a double bond between those 2 carbons, I got to get rid of the 2 hydrogens. So if I did that, I would end up with something like this. This would be considered an unsaturated hydrocarbon because those 2 carbons do not have the maximum number of hydrogens that they can have. Obviously, as you could probably tell, unsaturated hydrocarbons occur when you get into double bonds or triple bonds. And again, because you got to lose those hydrogens, so you won't have the maximum number of hydrogens present. Cycloalkanes, as I mentioned earlier, basically will join in a ring type structure. And again, they will also lose that extra couple of hydrogens to cause that ring to basically join up. And alkanes pretty much all have the ending ane. And let's talk about really the first 10 alkanes, which are really important. That is our carbon-carbon single bonds, and again, CnH2n plus 2. So CH4, that is our friend methane, ANE. C2H6, that is ethane. C3H8 is propane. C4H10 is butane. When you hit 5, it kind of goes prefixes at that point. C5H10, that is 5 is penta, so that is pentane. C6H12 hexa, so that is hexane. C7H14 is heptane or hepta. C8H16, that is octane. C9H18 is nonane. And C10H20 is decane. These first 10 alkanes, as I mentioned before, the name and the formula are really important because, again, everything does sort of fall back to those. You just sort of change the naming. As we saw earlier, we had our C2H6, which is ethane. We threw a double bond in there. Still based off of two carbons, which is ethane, but it has a double bond. So that's an alkene, E-N-E. So this becomes ethene, E-N-E. So really based off of that name. Also, when we threw our triple bond in there, this is again an alkyne, Y-N-E. And still based off of our two carbons. And that then becomes ethyne here, Y-N-E. So everything really does, in terms of naming, sort of fall back to these first 10 alkanes, or the alkanes in general. Also, even our sort of cycloalkanes in our ring structures, again, if we had our three carbons, this is propane. When we put it into a ring structure, which is a triangle in this case, is still based off of 1, 2, and 3 carbons, which is propane, but it's in a ring form, so we just put cyclo in front of it, and that would be cyclopropane. Just like here, this would be 4 carbons. 4 carbons is based off of butane, and it's a ring structure, so this would be cyclobutane. So a lot of things come back to these alkanes in terms of how things are named, and also different groups, even groups that are attached in terms of how they are named as well. So speaking of that, let's try. I'll take a look. When we look at something, for example, like look at each of these things here, for example, and we count up everything that we got going on. We have 1, 2, 3, 4 carbons. And if we count up all the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 as 10 hydrogens. That is 10, but I probably should put hydrogen first, huh? Let's try that again. I'm just going to blank the screen. It was just terrible. Let's try that again. There we go. Get that. Try hydrogen here. Hydrogen 10. There we go. We come over here. We got 1, 2, 3, 4 carbons. And we also have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 hydrogens here. These two things have the same formula, but they do have different connectivities here. And they are connected differently. And this is what is referred to as being isomers of each other. So isomers in organic chemistry are anything. Isomers are basically two things that have the same formula, but they do have different connection, and they also have different names. And we will pause on that and get into how we can tell the difference in lab, I think.